Examine the function f of x equals x minus ln of x for the following properties and use that info to sketch a graph. So we're going to start with the domain, and we know that because this includes an ln of x, the domain is not going to include the negative numbers or 0. So the domain here is going to be from 0 to infinity. Next up, we have intercepts. There is no y-intercept because our function is not defined at x equals 0. And if we wanted to look for an x-intercept, we would have to take x minus ln of x and set that equal to 0 and solve. And that is not the sort of equation that we have ever solved before. We could add ln x to both sides and get x equals ln of x, but we don't know when x equals ln of x. That's not a nice equation that we know how to solve, if there even is a solution. So we're going to skip that step here. And perhaps we will find some x-intercepts later, but it's not clear to me that that's something we can execute pretty easily right away. As far as symmetry goes, we don't have any graph on the left-hand side of the y-axis, so we're definitely not going to have any symmetry there. As far as asymptotes go, we should have a vertical asymptote because we've got that ln of x here. We know that this has an asymptote as x approaches 0. There is a second term here, but when x is close to 0, this term is also close to 0, so it is insignificant compared to this. And so we can expect a vertical asymptote at x equals 0. So vertical at x equals 0, which is the y-axis. For our intervals of increase and decrease, we're going to need our derivative, which isn't difficult to do here. The derivative of x minus ln of x is just going to be 1 minus 1 over x, which we can also write as x minus 1 all over x, because 1 is the same as x over x. So we have our derivative. If we're looking for critical numbers, this function is undefined when x equals 0, but since that's not a part of our domain, that's not going to be a critical number. The numerator is equal to 0 when x is 1, which means the function is going to be 0 when x is 1. So x equals 1 is going to be a critical number. We can make a sign chart to look at what's happening with our intervals. I'm going to put 1 there. I'm also going to put 0 here just because it's undefined to the left of 0, so we don't have to worry about that. And our factors for the derivative are x minus 1 and x. X minus 1 is going to be 0 at 1, and then above that it'll be positive, below that it's negative. X is always positive on these intervals, so our derivative is going to end up being negative and then positive, so we'll be decreasing and then increasing, and so we will have a local minimum at x equals 1, and when we plug in 1 for our function value, that's going to be 1 minus ln of 1. Ln of 1 is 0. E to the 0 power gives us 1. And so we're just left with 1 as our function value. So we've got a local minimum at 1, 1. For the concavity and points of inflection, we need the second derivative. And to do that, we need to differentiate the first derivative. And the easiest form of that is 1 minus 1 over x. Because if we use the other version, we would want to use the quotient rule, which makes it more complicated. The derivative of 1 is 0, and we just have to differentiate negative 1 over x. The derivative of 1 over x is negative 1 over x squared, but that other negative in front makes it positive. So we've got positive 1 over x squared. This is never equal to 0. So we're not going to have any critical numbers. In fact, this is always going to be positive on our domain. So that means that we're always going to be concave upward. And now that we have all of that, we can sketch our graph. We know we have a vertical asymptote on the y-axis. So I can put that in here. We know that we have a minimum value at 1, 1. We know that our function is going to be decreasing and then increasing and concave upward the whole time. And so for this first interval here, for it to be asymptotically approaching the y-axis and decreasing, we know it's going to be asymptotically approaching, going upward as we get closer to it. And this is also a minimum, so we know the derivative there is 0, so it's going to be horizontal before it starts going upward. And then on the right-hand side, it is increasing and concave upward. So it's going to be something like this. Don't know exactly how high or low it's going to be. So actually, let's use this to get one extra point so we can get a better idea, because we don't know where it's going to be going. So let's actually plug in a value. Let's figure out what is happening at 6, just so we can get an idea. So f of 6 is going to be 6 minus ln of 6, which is about 4.2 according to a calculator. So 6 comma 4.2 is going to be right there. So I'm actually going to go ahead and erase part of this. Don't hate me if you wrote in pen and you have to erase it yourself now. I'm sorry. I just thought this is a good example of a time where a point would be more valuable, because then that actually shows us that it wasn't quite as steep as we had thought at first. So there we go. That is our graph of f of x equals x minus ln of x.